nanohub.org.
Online simulation and more for nanotechnology.
So we're gonna move to a new subject. We have finally all the ingredients we need to cook up an uncertainty propagation problem and solve it. Basically, everything we did in the what we did in the past 3 lectures is gonna help us set up the uncertainty in this problem, and the way we're going to propagate this uncertainty is with Monte Carlo or with sampling methods. So have you heard about Monte Carlo before? Who has? Okay, good. It's very easy. All right. The idea is sample realizations of whatever is uncertain, plug them in, whatever is your model, and look at the quantity of interest. Okay. Repeat many times, as many as possible, and by looking again, do histograms of the quality of interest, basically. Okay, that's how it works. But we'll do a little bit of math to understand how fast Monte Carlo converges and how you can quantify the epistemic uncertainty when you have to stop it before you get convergent results. All right, so, and we're going to use Monte Carlo to also understand the emergence of the curse of dimensionality. I will explain what this is. And we'll define basically a very simple strategy for evaluating multidimensional integrals that kind of deals with the curse of dimensionality. This is going to be the core of Monte Carlo that we're going to talk about. This is something that you may have seen if you have taken a math course. Usually we ignore it completely. Monte Carlo can also give us an estimate of how uncertain whatever we compute is, and we're going to do that. And then we're going to apply this to a boundary value problem, ridiculous heat transfer problem. It's actually steady state. We're going to propagate through it the uncertainty of the conductivity field. Okay? All right, so estimating expectations of functions of random variables is enough to get to estimate any statistic of interest. Okay, so what I'm claiming is that it suffices to be able to evaluate expectations. So it suffices to be able to evaluate integrals like that. So imagine that you have a random variable x with a probability density p of x, and you know that probability density. This is what we have been talking about in the previous lectures, right? So what is x? Is it a field? Is it a parameter? You need to come up with a probability density for it. So let's say you have done that. And f of x doesn't have to be the model itself. It is a quantity that depends on an expensive or less expensive physical model. So to evaluate f of x, for example, maybe you need to do a finite element simulation. So when you say f, give me what is your value at x, then f goes and writes an input file, and then it calls MATLAB. But with that input file, then MATLAB finishes, and then you run a script that processes the results and gives you something that you're interested in. Okay, that will be f of x. And let's say, for example, and what I'm saying is that no matter what you're interested in, it can always be written as an expectation for a specific f of x. I'll show you some examples right now. All right, so obviously, if you are interested for x itself, right, you make f of x the identity and you get the expectation of x. You can be interested in the variance of x, and then you can make f of x x squared, and that's enough for getting the variance, because the variance can be decomposed with this formula. You may have another thing that you may want to compute, like the probability that x exceeds a specific value, right? Probability of the event that x goes beyond delta. That can also be represented by an expectation of this function. This is a an indicator function of this set. So it's 0 if x is not greater than delta, and it is 1 otherwise. This is the characteristic of that. But you could also do I have another example? Let me do one more example. So you could also do, let's say that you had a physical model that took x as an input and it gave you a y, and then let's say what you want is the probability that y is greater than delta, right? Not that x is greater than delta, but output of your model is greater than delta. Then that probability is delta to, it is a little bit stranger to write. I'm not going to write it like that. I'm going to write it like that. This probability can be expressed as the expectation of over x, because this is where you're taking the expectations of an indicator function delta to infinity, just like before, but here you put g of x. Okay, so this counts 1 if the output of your model is greater than delta, otherwise it counts 0. And if you take the expectation of that over all the possible x's, you will get the probability that y is greater than delta. But anyway, we will have the chance to meditate on that later on when we solve actual problems. But for the time being, the take-home message is expectations are actually enough, because anything you may think of, you can write it as an expectation. All right, now so let's focus on the evaluation of expectations. Somebody gives you a p of x, somebody gives you an f of x, find the integral f of x times p of x over all possible x's. This is a hard problem, especially when x is not 1 or 2 dimensional, and I'll show you why. Okay, so let's say that you are working with a random variable that has a uniform distribution in d dimensions. So it's a vector of d numbers between 0 and 1, and it is sampled randomly. You want to compute this expectation, this integral, all right? An integral over this hypercube. This is how it's called. How would you do it? Any ideas? How would you do it with what you should have learned in a numerical analysis class or numerics class? Gauss quadrature, Chebyshev quadrature, Riemann integral, trapezoid rule, Simpson rule, etc. Okay, with a quadrature rule, with a classical quadrature rule. Here's a classic. Let's do a classic quadrature rule in 2 dimensions. So imagine that we're integrated over the unit square. All right, for 0 to 1, 0 to 1, and our function is basically defined it's giving us values outside, coming outside of the screen. So it's like that. The function is like that. So what would you do? You would split the unit square in small boxes. Here I have, 100 boxes. Okay, and then you can go at each one of the boxes and ask, what is the value of f at the center of the box? Right? What is the value here? Let's say it is 10. Okay, let me approximate the integral below the surface over this particular box with the volume of a cube, of a rectangle. Oh, what is it really? It's not a cube. What is the right shape? Rectangular prism. Okay, good. A prism. Yes. So you do that for many different centers. So you go here, you say this is the value of f. You go there, this is the value of f. You go here, this is the value of f, and you can find the volume enclosed by these prisms, right? You add it all up, and that should be very close to the integral. And of course, the smaller you make these squares, the closer you're gonna get to the right answer. Okay? This is differential calculus. All right? Very, very old idea. Okay, so this is what you do. And in general, in d dimensions, you would use n equidistant points per dimension, and then you would take n to the d boxes, each with a volume that is equal to n to the power of minus d, or 1 over nd. And then you can evaluate the integral by that, by summing up the volume or hypervolume below each one of the hypersurfaces. Okay, so this is like the simplest possible quadrature rule. And it works for any d. As soon as you make n very big, it is going to work. Okay? But let's assume that it takes a millisecond to evaluate the function, to evaluate f of x. Okay, so you're going to have to evaluate f of x at the center of each box. So let's say it takes 1 millisecond. For d equals 2, if you use a 10 by 10 grid, you need to evaluate the function value at each one of the centers of the 100 boxes you're going to have. So you're going to need, okay, a little bit less than 1 second, okay? Like a tenth of a second. For d equals 3, you will get something that is 10 times what you get for d equals 2. For d equals 5, 10 times what you need, actually even more than what you need, 10 times what you need for d equals 3, times 10 as well. For d equals 6, okay, I made a mistake. Everything is an order of magnitude wrong, but okay. Like divide by 10 all my numbers, okay. So for d equals 6, you will need approximately 15 minutes, even though the evaluation of the function takes a millisecond. And then for d equals 10, you will need a few days, like a week. And then if d equals 100, you cannot really do it. You're basically getting to the point where you need the life of a universe to actually do the integral. Okay? So, and it's obviously, this is a ridiculous way to evaluate integrals. It doesn't scale. And it doesn't scale very fast. Extremely fast. Even d equals 6, it's something that you can barely do. D equals 100, you can just forget about it. It's not happening. All right, and most of the problems that are of engineering interest are actually below this point. You have not d equals 100, but you have d equals 1000 or 10,000. All right, so we forget about that. It doesn't work. And this is where the Monte Carlo comes and Monte Carlo estimates come and save the day. And I'll explain why they don't really depend on the dimensionality of the problem. This is their property. But I'll show that later. So here's how Monte Carlo works. You want to calculate an expectation of an f of x. So the integral is basically an expectation. And of course, the expectation is what you expect to get if you sample repeatedly and take the average, right? And this is actually what happens. So there's a theorem that is called strong law of large numbers that says that if you have independent copies of your random variable and you evaluate on each one of them f of x, and you sum it all up and you divide by the number of samples you take, this average here will converge to the expectation of f of x over all the possible x's. This is just a theorem. And this, when you deal with random variables, there are like 4 or 5 kinds of convergence. There's the almost sure convergence. There is the convergence distribution. There are even weaker there is convergence in expectation. There is weak convergence. This is the strongest possible convergence you can get. Okay, this convergence, the almost sure convergence. Yeah, and these are the assumptions of this theorem, meaning there are no assumptions basically. You just have to get independent samples of your x's, plug them into f of x, take the average, that is going to converge no matter what to the expectation. It makes sense, right? No, sufficiently ugly f. Could be very, very, it converges for f that are strange. Converges for, okay, can you come up with a very, very weird f? Maybe, but it is very unlikely that you will encounter one f for which it does not hold. Extremely unlikely. This doesn't mean that it is a good estimator, as I will show later on, because unless f is good, this may have an infinite variance, okay, as an estimator. We will explain that later. But for the time being, find me a case where it doesn't work. Look up the theorem, see what is what you have to assume for f, and I would argue that you will have to find a very strange f for which it doesn't hold. Okay, so let's apply this idea to a very simple problem of 1D integration. So we have a uniform distribution between 0 and 1, and we have this f of x, this made up f of x, and we want to integrate it. Take the expectation of f of x. So to give you an idea of how this f of x looks like, it looks like that. Okay, so it's not simple, but it's still one-dimensional. And the way we're going to Monte Carlo evaluate it is basically just take samples. The value, it takes samples of x, it looks at f of x, right? And then it just takes the average of that. Okay, and that will converge to the integral, to the area below the curve that you see here. And of course, the reason that I picked this ridiculous example is because we know exactly what we're supposed to get. So, you can see that it converges. Okay, so here how the average, the Monte Carlo estimate evolves as a function of the number of samples you take. So if you take 10 samples, then your estimate is right here. If you take 100 samples, you see your estimate up there in the blue. And the correct value, of course, is a straight red line. And you see that the blue line, very quickly goes very close to the true value, but then it kind of strangles, jumping around. It doesn't quite make it for 1,000 samples, okay? So you may wonder, maybe it doesn't really work, but if you take more samples, like 10,000, it actually nails it. Okay, but still, you were a little bit worried about the fact that how do we know if you don't really know what the red line is? How do you know where to stop? Right? How do you know that you need to go to 10,000 to get an accurate estimate? Maybe, if you don't know the red line, maybe you can stop prematurely. You can be fooled by this running average. So let's see what happens. So for n is small, you see that it is not an accurate result, but if you don't know the truth, you may be fooled and stop before actual convergence, because it flattens up and moves very slowly, and it may fool you to think that it's actually done when it's not done. And as a matter of fact, if you take a completely different sample, so if you start from scratch, you will get a different curve. So you see these two curves, they look completely different. I mean, they kind of converge to the red line, but you don't know the red line in reality. Okay, that's the point I want to make. Anyway, but here's what you start seeing if you take 10 samples. If you do this thing 10 times. So you see 10 times, you get 10 different Monte Carlo estimates that kind of envelope the truth. Okay? Yes?
With the same data, or you pick 1,000 different?
1,000 different, I mean, this is actually, this is the running Monte Carlo estimate, running in the sense that I'm gradually increasing the number of samples I'm using, okay? And this is 10 different repetitions of this thing, completely independent, So you start from scratch. So you do, let's say, the purple line, you start sampling, and every time you sample, you update your estimate. Done. Then let's start from scratch and do the red one, and you do the same thing. But you see that if you run it 10 times, it kind of goes around and embraces the truth. And if you run it 100 times, you start seeing something like that. I mean, you can clearly see that it doesn't close the truth. And that happens if f is sufficiently smooth, okay? Now, you need the smoothness of f to get this nice enveloping property. I'm gonna break it down next time. But the question is, you know, nice, if I run it 100 times 1000, I can get this nice envelope, but this may be something that I cannot afford in my example, right? So can I get this envelope without running the whole thing 100 times, right? Can I just get one of these lines and get some error bars around it? You see what I mean? So what if you just take one of these? Is there any way to produce epistemic error bars out of one Monte Carlo sample? And yes, there is. And for that, you need the central limit theorem. This is how you do it. Now, for the central limit theorem, you do need f to be nice. And by nice, I mean that it must have a finite variance. Alright, so that's how nice it should be. So it can still be ugly as soon as it is square integrable. But you don't need that for the strong law of large numbers. Anyway, so slightly abusing the notation, the central limit theorem, which is something that we talked about in lecture 2, perhaps, or 3, right? Remember what it said? It said that if you take an independent random variables that have a finite variance, and you sum them all up, and you divide by and you take the sampling mean of them, all right? That sampling mean will go closer, will start looking like a Gaussian. This is what the central limit theorem says. So here, applying the central limit theorem on f of x, and assuming that f of x is a random variable that has a finite variance, then the central limit theorem tells you that the running average, the sampling average converges in distribution, so this is a different kind of convergence, to a normal distribution with a mean that is basically the expectation of whatever you're summing up, and a variance that is 1 over n, whatever is the variance of these guys. So this is just a theorem. And so how do you interpret that? You can interpret that as follows. If you repeat this thing 100 times, this is how, and so if you go and take the sampling average, not up to 100, but you take it up to a large number, let's say 1000, but you repeat this thing 100 times, chances are that, not chances are, the distribution of what you're going to see is going to be this Gaussian. But let me show you how this looks like. Okay, let me repeat this. It's a typo. So you can use the central limit theorem to say my estimate about this expectation is basically the Monte Carlo estimate plus minus 2 times the standard deviation of the variance. Okay? The problem is that we don't know what this variance is. This comes from the central limit theorem. The central limit theorem guarantees that I will be 95% of the time inside here. The problem is that this, we don't really know it, so we're going to have to estimate it. And you can estimate it with yet one more sampling average. So the variance that you need for the central limit theorem, you don't know it, because it is also some kind of expectation over the square of f of x, actually. But you can estimate it with this estimator, for example, another Monte Carlo estimator, and then you're done. This is it. So you can say that with 95% probability, the expectation you're looking for is going to be plus or minus 2 standard deviations divided by square root of n around the Monte Carlo estimate. And here's how it's going to look like if you plot this estimate. So now I'm just taking one running Monte Carlo estimate, the blue line, and at each point of this blue line, I'll give you -2 and +2 standard deviations divided by square root of n. Okay, so this is the right estimate. And you see that at the beginning, the truth is not inside, okay, but at the beginning, the central limit theorem doesn't really hold, because the central limit theorem holds for relatively large n. But when the central limit theorem kicks in, and it kicks in around here, okay, around n equals 100, then these epistemic error bars do include the truth. Okay, so now you do have a way to decide when to stop. You just have to look at the spread of these epistemic error bars. Okay. By the way, how many do here MD simulations? Only Ricky? Okay. So this is what you can do to decide when to stop sampling. Okay. If you want to get the average potential energy, average kinetic energy, you can actually derive this error bar and decide when to stop sampling, or for any other quantity for that matter. All right, and here's another sample completely from scratch. You see that again, this epistemic uncertainty does include the truth. And this is what happens for bigger n. So as I increase n, this epistemic uncertainty collapses. And here you see the epistemic uncertainty that I got from one of these samples, probably one inside here. And then I just drew another 10 or 20 samples, and I just put them all together just to show you that they're all inside, more or less, these epistemic error bars. And they have to be inside. They have to be inside with 95% probability after the central limit theorem kicks in. Okay, so what is the moral of the story? Doing Monte Carlo without producing these epistemic error bars, it's probably a stupid idea because you don't know when to stop, and if you repeat it again, you'll get a different answer. Unless you have stopped after a very, very, very big n. Okay, but if you are quantifying the epistemic uncertainty using this thing, then you can monitor it and decide when to stop if it has been reduced below a certain threshold that you can set. Okay.
Do you calculate the variance of that?
Yes. You are gonna be uncertain about that as well.
So then you draw a figure using the variance.
What was that?
You draw a figure.
These epistemic error bars do depend on the variance of f, which we do estimate also with Monte Carlo, right? And we are also uncertain about that, but this is like a second order effect in our uncertainty about the expectation of f of x. Right, so this is a subtle point that I don't wish to make, being afraid that I may confuse you more than enlighten you. So I'm going to not elaborate any further on it. But I'm willing to discuss it. It's actually a very good point after class. All right, so Monte Carlo helped us to deal with the curse of dimensionality. Sort of, and I'll explain what I mean by that. So first of all, why is Monte Carlo good at dealing with the curse of dimensionality? The answer is this. The answer is that the epistemic uncertainty that you get for whatever you're estimating with Monte Carlo does not depend on the dimension of x. The dimension of x is nowhere to be found there. It is always a constant times 1 over square root of n, where n is the number of samples you take. So no matter what kind of problem you have, no matter what is the dimensionality of the problem you have, your Monte Carlo estimate converges to the truth as 1 over square root of n. There is one constant in there which can be quite large. This is the constant, and it can be quite large in practice, but it doesn't really depend on the dimensionality. And that's why Monte Carlo estimates are routinely used when you do molecular dynamics or statistical mechanics. Actually, Monte Carlo was invented to do statistical mechanics. Okay, it was invented at Los Alamos to do statistical mechanics. And the reason that in statistical mechanics, the dimensionality of the space, it's basically the coordinates, the generalized coordinates of your molecular system, which is 3 times the number of atoms that you have, which can be huge, like millions or even more than that. Okay, so you cannot possibly do the integration with any other technique but this. Okay? And even in these cases, you can't get good estimate of these high-dimensional integrals. High-dimensional integrals in molecular dynamics would be integrals that give you the potential energy, the average potential energy, the average kinetic energy, or heat conductivity, for example, for more complicated simulations, etc. And you can produce reasonable estimates with reasonably small n. But still, you have to sum up to a big N, but it is reasonable for if you take into account the dimensionality of the underlying system. All right? Yes?
So the N does not depend on the essentially the number of samples after which the central limit theorem you think it does not depend on the dimensionality at all.
No, it doesn't. But you... So the central limit theorem kicks in almost immediately unless you pick an n that is ridiculously small, like 10, 20, 50, right? But if you use n equal to 1000 or 100 and you don't have a weird problem, you'll be fine with this estimate for the uncertainty, for the epistemic uncertainty. Any other questions? Yes.
So how is quadrature different from Monte Carlo? I mean, we are just taking random samples, and in quadrature we take uniform samples. So
in quadrature, you don't necessarily get uniform samples. This is one type of quadrature, right? Monte Carlo is another type of quadrature. Classic quadrature rules that specify exactly where the quadrature points are and specify exactly the weights of the quadrature points do not scale in high dimensions. And they just don't work. The number of quadrature points explodes with the dimension of the space. There are some quadrature rules that are better suited for high dimensions, like sparse grid quadrature, but this blows up as well. So the only thing that doesn't blow up is Monte Carlo. Everything else does depend on the dimensionality of the space.
So for one dimensional problem, if we take enough sample points for quadrature, it should converge to the
Yes.
same thing as Monte Carlo.
Yes. I mean, okay, so here's how it goes. Monte Carlo in one dimension is something that you should not do. Okay? Because it's one dimensional. So you better do, I don't know, the trapezoid rule. Okay? Or Gauss quadrature. Because they are more efficient in one dimension. In two dimension, you should probably also not use Monte Carlo. But try defining a quadrature rule for a molecular dynamics problem where you have to integrate over the positions of all the atoms, which would be in the millions. You cannot define a quadrature rule there. I mean, you can in principle, but it's going to have more quadrature points than the grains of sand in all the beaches of the earth. And even probably even more than that for a realistic system, right? So there's no quadrature rule that doesn't blow up as the dimensionality of the space over which you integrate, except this. But this constant may be very large. So convergence may still be slow, but at the end of the day, it will beat anything else if you start increasing the dimension. All right, so for a fixed dimension, if you spend like 4 years doing a PhD on how to do that particular integral, you may be able to find a faster way to do that integral. And then, you go to another problem, you have to do it from scratch because it just doesn't scale. Okay? This is just how it is. Okay. And this is a good point to remember. Monte Carlo goes down like that. 1 over square root of n. Yes?
Is it still 95% because the variance is estimate.
Yes, so this is a subtle point that I don't want to make, but let's make it. So, here's how it goes. The problem is that the central limit theorem guarantees that with 95% probability we're going to be within specific bounds if you know exactly what the variance is. The problem is that the variance itself is a Monte Carlo estimate, so you are uncertain about it. Okay? So what I argue is that if you do the math and you look at your epistemic uncertainty about the variance, this is going to be a second order effect on that uncertainty, which you can ignore.
So
unless you want to spend time on that.
Is it still 95% or less?
It's with 95% probability around 95%. So it's a second order effect. I cannot guarantee that it's going to be exactly 95%. If you notice, if I wanted to be extremely rigorous, I would not put in here 2, I would put 1.97. I made it 2. Okay? So I actually made it a little bit broader. Hopefully that accounts for the fact that I don't know this exactly. Right? But I don't worry too much about this.
Is it 95% square?
Is it what?
The confidence. 195 square.
Okay, I'll tell you what. Bonus exercise, derive the uncertainty for the Monte Carlo estimate of the variance and see how it modifies and what kind of order effect you get on this estimate. And my guess is that it's going to be, the correction is going to be less than 1 or 2%, and it can be ignored. And the bigger n becomes, the smaller it will become. Okay? Because what you would do, you would go here and you would say parenthesis, estimate of that plus or minus 2 times 1 over square root of n of something, so the correction would be 1 over n. Ignore it. Okay? All right. These are good questions. I love these questions. I would do it if I didn't have to teach the class. I would actually do the derivation with you. Any questions? Any other questions? All right. So let's see practical application. This is the first uncertainty propagation problem that we can cook up. And here's how it goes. We have a steady state heat equation. So you can imagine that you have a rod, okay? And one side of the rod, say the 0 side, is at temperature 1, and the other side is at temperature 0, okay? So you want to find the temperature distribution in between. And the only complicating factor is that your conductivity, your thermal conductivity, C of x, is a function of x. So it's not constant. If it was constant, then you don't even have to solve the equation. You know it's going to be a straight line going from 1 to 0. Okay? But now because the thermal conductivity changes with x, it will vary slightly. It will still go down. It will still be around the straight line, but it will not go exactly as the straight line. So what we're gonna do, we're gonna do a little bit of UQ to quantify our uncertainty about the conductivity, but this is not serious UQ, and this is not how you should do it. I'm just going to assume a model for it, and I'm going to assume a model for it that is actually very far away from the actual model that you should use, which should depend on how you made the rod. I'll just pick up one model that gives me complicated behavior. All right, but this is how it looks like. So I'm going to assume that the conductivity is some constant function of x, constant in the sense that there's no uncertainty in that function. And as a matter of fact, I'll pick this to be 1. Okay, I'll just pick this to be 1 times the exponential of a random field. Okay, because I know that the conductivity has to be positive. So I'm going to model it as the exponential of a random field. And that random field, I'll take it to be a Gaussian random field. Okay, with a specific covariance function that decomposes like that, the Karuna-Loew expansion of which is like this. All right, this particular covariance function gives rise to what is known as the Wiener process or the Brownian motion, and it's actually a nice covariance function. It's a non-stationary covariance function. If you compare x and x prime, it is basically just some sigma times the absolute value between x and x prime. So it just tells you that things become less correlated as you go away from, if you look at measurements of the function at 2 points that are far away, uncertainty, correlation changes in this way. Actually, this is wrong. This is very wrong. Let's put a question mark, okay? And I don't remember it. I'll come back to it later. But it's not that, unless I was lucky guessing it. But anyway, what I'm sure about is for that particular Gaussian random field called the Wiener process, I can describe it to you. Here's how the Wiener process works. You start from function value, let's say here at a specific x, and then if you want to move to a next that is a little bit next to where you stand right now, you add a little bit of Gaussian noise. And then if you want to move to another x, you add a little bit of Gaussian noise. But you make this interval of x is very, 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 very thin to the point where it becomes continuous, and then you get this Brownian motion. I'll show you how it looks like. The reason I'm using it is because the Karuna-Loew expansion is very simple for the Brownian, for the Wiener process. It's actually completely analytic. Okay, so I don't have to do the Nystrom approximation and all that in our first uncertain propagation experiment. Okay, that's the only reason. All right, and in principle, you're supposed to retain all the dimensionality of the size, but I'm going to truncate it at a finite order. But you'll see right now that that finite order will have to be quite large. It will have to be of the order of 1,000. So this is how the samples from the Wiener process, actually the exponentials of the samples of the Wiener process look like for d equals 10. If I just retain 10 terms in the Karuna-Loew expansion, they are very smooth. But this is not the truth. You should really be increasing d until you stop seeing differences. So if I make d 100, then I get this. And this looks way more complicated than before, but it still hasn't converged in terms of, you know, how many wiggles it can do. And you can make d equals 1000, and then it kind of starts to take the shape of a true Brownian motion. Okay? But no, this particular model, remember, it is not Brownian motion itself, it is the exponential of a Brownian motion, okay, that starts at this point and then it just does crazy things. But this is the model that is used in to model stock prices. It's the exponential of a Brownian motion plus a constant drift. This is the classical model that is used there. But you really need to keep 1,000 random variables to describe it. You cannot describe it with fewer variables than that. And as a matter of fact, this is also not enough. You actually need all of them. You can show that you need all of them. Because another characteristic of this thing is that if you zoom inside one of these regions, you will see exactly the same complexity that you see in the full picture. And then if you zoom here and you magnify it and you zoom again, you will see exactly the same complexity, and it never ceases to be this complex. So this is one example of a process whose samples are actually self-similar if you zoom inside them. I'm not sure if things like that exist in nature, but I mean, to the point where every time you zoom in, it always looks the same, no matter how much you zoom in. It may be just a mathematical artifact, but this is how this thing looks like.
Why are we increasing the D here?
Because the true process that I defined has an infinite number of random variables. Come on. Has an infinite number of random variables, and you have to truncate it, but you cannot just truncate at 10 because it looks very different than what it is in reality. You cannot truncate at 100 because it also looks very different, and at 1000 or higher, it kind of looks similar for the resolution that we have, okay? But what I'm saying is that if you zoom in further, you will realize that you need more points because it is way more complex than you see.
What do you mean by similar here? So this is for D1000, we are getting 10 samples.
Okay, so here's what I mean. If you go here, in this region, and you magnify it, and you look at it, it will not look smooth. It would look as complex as the big picture. And if you then go to this place and you further magnify it, it will also not look smooth. It will look as complicated as this. Yes?
Isn't that a characteristic of a chaotic system?
It is a fractal. It is a fractal. But I'm not sure if it corresponds to anything real. That's what I'm saying. Because it's just a mathematical artifact. This is how this process looks like. Okay, you can spend a semester studying just that.
Can't we take energy of the field and fix the D?
Yeah, so if you take the energy of the field, it's going to be infinite. Right?
0.95 times old.
It doesn't work. All right. So, anyway, this is just our model for our conductivity, okay? It is not a real model. This is not how you should create a model, but it is a model that we're going to use to do a little bit of Monte Carlo. So, we're going to implement a solver for the steady-state heat equation using the finite volume method. And I did that using PhiPy, which is a Python package that does finite volumes. And you should think of PhiPy as if it gives you the map between Xi, the set of these random variables, and the temperature at every point you may want it. Okay? So you think of this as a map from Xi to the temperature. And this is how samples of the temperature look like if you pass them through the finite volume solver. So here I sample a bunch of Xi's, which corresponds to one of these crazy lines that you saw for the thermal conductivity. I take that thermal conductivity, I go to the finite volume solver, I solve for the temperature, and I get one line, one of these lines, and I repeat 5 times and I get 5 different answers. Okay? And what we want to study is the statistics of this response. Okay? And this problem, it is a ridiculous problem, but no uncertain quantification technique except Monte Carlo can solve it. Okay? Because it is 1000 dimensional. even though I can guess the answer very easily. The mean of the temperature field is going to be a straight line going from 0 to 1, okay? Because of symmetry. And by all means, you should be using your intuition like that to do it. And also I can guess the uncertainty. The uncertainty is going to be small here, it's going to grow as you go to the middle, and then it will become small again. But anyway, let's use Monte Carlo to calculate the expectation of the temperature at the center of the domain. So this is the thing that I'm looking for. I'm going to call it the mean of the temperature at x equals 0.5. So this, I turn it into an integral. It is basically the expectation over xi of that function, the temperature as a function of xi, or integral over xi. Okay, so this is the temperature I get from the finite volume solver for a given xi, and I want to integrate over all the possible xi's. This is the integral that we need to do. This approximate here is because I'm actually truncating. I'm not taking the infinity of the size, but I'm taking fewer than infinite. But anyway, you could use do your Monte Carlo estimate with the corresponding uncertainties, and it would look like that. And of course, you could guess, because of the symmetry, that in the middle the temperature would be 0.5. It is 1 at one end, 5 at the other end. The samples of the thermal conductivity are more or less symmetric. And you have to get 0.5, so you do get 0.5. Alright, but there are more things that you may want to do. You may want to visualize your uncertainty about the temperature samples themselves. So you can think now of the temperature itself as a random field that is induced by the random field that you put on the thermal conductivity. So, and some of the things that you may want to do, one of the things that you may want to do is, for example, the median. Get the median of the temperature field. So the median of the temperature field is defined basically by this equation right here. It is the mu of x. It is the mu of x that has the following property. The probability that the actual temperature is smaller than the mu of x is 0.5. And of course, the probability that the actual temperature is greater than mu of x is also 0.5. So it's kind of like a temperature line that is kind of central. And you can estimate this very easily using Monte Carlo, but I'm not going to give you the estimator. You can look it up on Wikipedia. I'll give you the formula in Python that you can use to do it. What else? And the other thing that you may want to visualize are the Q quantiles. So instead of looking for the median, you can look at this at an arbitrary quantile, or called the Q quantile, and this mu of Q is such that the probability that a path of the value of the temperature field is below this mu of Q is Q over 100. So you can use that to bound the temperature field. You can make Q, for example, there 2.5 and get a lower bound of the temperature field. You can make it 97.5 and get an upper bound for the temperature field. And of course, for Q equals 50, you get the median. And, that's how you bound your solution. You find these guys, the 2.5 and the 97.5 quantiles from samples. Okay, so there are Monte Carlo estimators that can give you these quantiles if you have samples of these functions. And that's how they look like, right? So the 2.5 quantile should go at the bottom, the 97.5 quantile goes up there, this is the 50% quantile, and then everything should be in between. If you take 100 samples of the temperature fields, 5 of them only are going to be outside of these bounds. Okay? Now, the reason why these are a little bit wiggly is because we have used a finite number of Monte Carlo samples to estimate them. So you see, so we do have a little bit of epistemic uncertainty about these, but this is a second order effect that we just ignore. Okay. Now, if you do this and you start seeing things like that, you probably need to get more samples. And you'll have the chance to play with this in the handout. We have 15 minutes to do that? Yes. Another thing that you can do right now is compute the probability of a rare event. You can say, for example, at this particular x, what is the probability that the temperature exceeds a specific value? What is the probability that temperature goes beyond 0.8 at x equals 0.5? And this is also an expectation, and it is this expectation. And I mean, you can construct a naive estimation of this using Monte Carlo, 1 over n, sampling average of whatever is inside there. And it will look like that, okay? It will look like that. Well, you see, it is very, at the beginning, it is not very good. It becomes better and better. But don't be fooled, because the probability of a rare event is a very hard thing to compute. And this particular event is not a really rare event because it has a significant probability of occurring. If it was very unlikely to occur, if it had a probability like 10 to the minus 3, for example, or 10 to the minus 6, this will give you utter garbage. Okay? But in real applications, when you're designing things for with specific requirements, like for example, guarantee that 99.9% of the time it's going to be, your system is going to be operational, the probabilities that you're going to have to compute are very, very small, and Monte Carlo does not work, and then you have to do something else, about which we're going to talk next time. Okay? So, yes, Monte Carlo works for pretty much everything you want to do. It scales independently of the dimensionality of the space, but don't blindly apply it to things that are a little bit strange, like to compute numbers that are expected to be very small, for example, or numbers that are expected to be very big. Don't apply it blindly. You need to think about it. All right, so let's spend now 15 minutes to go over the hands-on examples where you're supposed to pretty much replicate all the figures that I have and answer some questions.